Hey everybody, AJ Campbell here. I am Texas Green Tea on Twitter, and this is the Lexting interface up close and personal. It's the fastest way to do text entry in VR and AR, and it also works on desktop computers. The private beta is coming up in Q1 of 2022, and you can sign up at lexting.com, but I got a lot of requests to provide more detail as to how this system works. So in prep for that private beta, I'm going to put a handful of tutorials on YouTube. I'm going to try and share about one tutorial per week until the private beta launches, so by the time you can download this interface for yourself, you'll be able to hit the ground running by watching these videos beforehand. This first video is going to be an introduction where I explain why I built the interface this way. And then in future videos, we're going to explore how Lexting works, how you can use Lexting to type entire words in a fraction of a second, like this. This is an interface built for speed. I designed it to be faster than QWERTY, not just virtual QWERTY, but all versions of QWERTY. Anyone who has used QWERTY in VR knows that in VR it's very slow, and so I spent a lot of time analyzing all of QWERTY's flaws, and then I went and corrected them. I'm sure a lot of people are wondering why I didn't just find a way to make QWERTY better, and the truth is, QWERTY can't work better. It's designed to not work in 3D, and here's why. Number one, small keys are highly error-prone, and number two, large keys take a long time to find, reach, and activate. If you wanted to touch type in VR, you'd have to make the keyboard the same size as a physical keyboard. QWERTY was originally designed to fit the average size of 2 human hands, but look how big each of these keys are in Oculus Home, for example. And I consider Oculus Home to be one of the best implementations of the QWERTY keyboard that there is. But as you can see, the keys have to be massive in order to prevent mistakes. If you try and touch type with all fingers on virtual keys that are the same tiny size as a physical keyboard, you'd hit the wrong keys all the time. That's why Oculus had to make these keys huge. Have a look at this. It's wider than my shoulders. You definitely can't reach the whole thing with 2 hands. And if you back up enough, then the keys get really small in your field of view again, so there's just no way to win. You have to revert to pecking with just your 2 index fingers. Or if you have controllers, you can use laser pointers instead, but that's essentially the same thing. No matter how you slice it, you used to have all 10 fingers in the game, and now you have only 2. And that's why your speed on a virtual keyboard is 75% less than the speed you have on a physical keyboard. Now picture yourself trying to write an email, but you're 4 times slower. Picture yourself trying to do anything at work, but you're 4 times slower. This is the roadblock that stops VR from working in an office setting. So either we have to stay chained to our desks forever because we need the physical keyboard, or there may be a non-QWERTY way that we can unchain ourselves from the desk, a way that'll let us type quickly, whether we're sitting, standing, or even walking. I actually wasn't sure how to fix QWERTY at first. I went through 3 completely different prototypes, all built from scratch, before I figured out how we can move way faster than QWERTY. It was a lot of trial and error, but in retrospect, the method is clear. It requires us to think about UI in a very different way. Usually, when we say UI, we're thinking about all the common elements we see on other devices: windows, icons, menus, and pointers. This is a super common collection of metaphors that computer scientists have been arguing over ever since the 1980s. Together, these familiar metaphors make up an acronym. We call it WIMP. These 4 ideas are the core of every operating system on every computer I've ever used in my lifetime. But there's a huge problem with all of these. These metaphors are not ready for VR and AR. And it's because they're flat. They're 2-dimensional. These exist on surfaces. And this is the problem that causes QWERTY to be slow, and I'll show you why. Let's look at QWERTY one more time. Every element here is on a surface. All QWERTY is a big collection of buttons, right? And we saw how if the buttons are smaller, they're closer together, easier to reach, and that's the core of our problem. We can't make the buttons small. If we do, then we hit the wrong ones a lot. But big is wide and wide is slow. So we need them closer together too. It seems impossible to have both of these things only because we assume that all the buttons have to stick to this one flat surface. But what if some of them were in front of others? What if some of them were behind others? Then we're changing the game layout-wise, because you can take some of the elements that were far off to the side and bring them closer to the center. Every element is suddenly reachable with much less hand travel distance, and that is one of the keys to picking up speed. But there's a problem with this. If you 3Dify a certain aspect of your UI, all the other aspects are still 2D-centric. The cursor, for example, is only going to work on surfaces, so none of the other parts of your UI will work with this new layout. You actually have to 3Dify everything in order to make this work. I'm going to show you what I mean by bringing up this list of metaphors again. WIMP stands for Windows, Icons, Menus, and Pointers. Depth is the new thing in spatial computing that didn't exist on desktop computers or touchscreens, and that's why none of these metaphors can do depth. In order to utilize depth, we have to 3Dify every single one of these. These were all built for surfaces, and we have to redefine them for volumes instead. Check this out. If you start with a window and then extrude it along the depth vector, you have a zone. Zones have volume, windows don't. If you start with an icon and extrude it, you have an object. Objects have volume, icons don't. If you start with a menu and extrude it, you know where this is going. You have a matrix. Matrices have volume and menus don't. And last but not least, and this one's very important, if you start with a pointer cursor and you extrude its ability to move, you have a point cursor. Now I know that's a lot of detail, but we're just going to zoom in on a couple of important parts of it. Extruding windows into zones is fairly obvious. Extruding icons into objects is kind of a smaller version of the same thing. But this does get confusing when we get to menus. Let's zoom in right there. A menu is just a list of choices. A list of choices can lay out in all kinds of ways. We can lay out a menu in 1 dimension, 2 dimensions, 3 dimensions, whatever we want. Let's try that on the x-axis with these buttons that each represent a letter. These are keys on the x-axis, laid out left to right or right to left. Or we could lay out the same menu on the y-axis, top to bottom or bottom to top. You can easily see how both of these are really bad options when you try and lay out a QWERTY keyboard, because if you only use 1 dimension, the keys stretch out so far in one direction that you'd never reach them without a scroll bar. And it would be silly to have a scroll bar in this situation because you need to access all these buttons rapidly. So 1 dimension is obviously not enough. And that's why we often lay out menus in a table fashion with 2 dimensions. When you use X and Y simultaneously, you multiply the number of options that you can fit on the screen at the same time. When your menu is 2-dimensional, it forms a grid that allows you to bring more of the content within reach. But like we saw, sometimes that is still not good enough in VR. For QWERTY, this layout yields a user experience that is way slower than its physical counterpart. So why don't we use the same idea again? Let's go to a higher dimension one more time. We're going to go from 2D to 3D this time. Now, if we place a hand in the center of this cluster of buttons, every single button is much shorter a distance away than before. We have elements available on the x-axis, the y-axis, and now for the first time, the z-axis as well. When we use all 3 axes, we shrink the total travel distance for our hands. But we've still got a problem when we try to highlight these elements. If we do so in the common way with a laser pointer, we have to cast a laser beam from our hand to the target. But see, there's the problem with pointers. The cursor is 2-dimensional. It can only touch the surface of the frontmost element. It can't touch anything behind that. So how do we fix this? We need to extrude the cursor's ability to move through depth. See, a pointer cursor can only move left, right, or up, down. That's 1 dimension and 2 dimensions. It can't move forward or backward. When my hand moves forward and backward, the cursor does nothing. I want to move it to the back of the UI because I know there are elements to access back there now, but my cursor just can't do it. So we have to throw away this idea of casting a laser beam out of our hand, because that's what causes the cursor to skip all of this empty space. This empty space, this depth substance, is our new UI space. It's part of our canvas and we are skipping it right now. And it's because we're thinking in surfaces when we should be thinking in volumes. Regular raycast cursors don't work on volumes. So the fix is pretty simple. All you have to do is pop that cursor off the surface and let it follow your hand in all directions, not just left, right, and up, down, but forward, backward also. See, now the cursor is no longer a pointer. Now it exists at a certain point in 3D space, and that's why I call it a point cursor. And point cursors are not a new idea. They were invented decades ago, but they're very uncommon in UIs today, and we need to fix that for any spatial UI that needs high performance, like Lexting. See, I needed a cursor that was able to handle multiple layers of depth so that I could utilize this new matrix layout, which is way faster than 2D layouts. So to recap, we've now 3Dified all these metaphors: windows to zones, icons to objects, menus to matrices, and pointers to points. We've created a new acronym. It's called ZOMP: Zones, Objects, Matrices, and Points. ZOMP is the name I'm using for this shift where we make everything about legacy UI 3D instead of 2D. Lexting is a ZOMP-style interface. It was created with ZOMP methodology, and it's important to remember that Lexting had to be ZOMP because ZOMP is a huge part of why Lexting is faster than QWERTY. So I think that's enough detail for the first tutorial. In the next video, we're going to be going over the basic controls, and we're going to see how Lexting uses the multitasking capability that's built into our hands for an even greater speed boost on top of the one we already got from ZOMP. So stay tuned for the next video, and remember, the future is now.